This is during work with Paul. So here is what we teach our juniors, that the world looks like this, that there is all these nice round problems that we can solve by efficient algorithms, and then there are some other annoying problems up there that we'll tell you about, okay? So, in reality, what happens is that just about every problem we touch is NP-complete. There are pitifully few ideas that for efficient algorithms, the ellipsoid is convex optimization, okay? So, and everything else is solved by. And there is a dark mass of problems that can be solved by heuristics and deep nets, okay? So, but, okay. That's a problem, but I'm not going to talk about this problem, okay? I'm going to talk about another problem, that there is a different kind of dark mass, okay? Ladner's theorem tells us that the picture is like this, okay? That NP-complete and P are the limits of a sequence of equal volume classes, okay? And so, given that life is finite, it's a miracle that we see any problem in P or NP-complete, right? I mean, the vast majority of problems, infinitely more often, we should see intermediate problems, okay? So, and we don't. So where are those intermediate problems? Well, they exist. Okay, if you don't know some of these, don't worry. So, I do. So, I have them. So, and the point is that they are hard. They seem to be out of P because otherwise, but they cannot be NP-complete. Because then our world, by world I mean the polynomial hierarchy, would collapse. Okay? Okay, and it turns out that with the sole exception of graph isomorphism, all of these belong to a class that we sort of can start understanding. It's called TFNP, total function, because in all of this a witness always exists, okay? And so the real picture sort of seems to be like this, okay? The sanitized picture, that there is P, there are NP-complete, and then there is this interesting class of seemingly intractable problems, in the sense that we don't know how to solve them, that are total, okay? And graph isomorphism. So, the question is, we would love to prove intractability for this, okay? How do you prove intractability? And the first, of course, reaction is to prove them TFNP complete. But it turns out that it's a non-categorical or semantic complexity class, and therefore, under oracles, it does not have complete problems. So this seems like a dead end. And here is the recipe. To classify a total problem in TFNP, look at its proof of totality, okay? This is an existential. It says for all graphs, there exists something, right? I mean, for all games, there exists something. So look at, it's an AE formula. Look at its proof of totality. And if it is constructive, so, you're out of luck. It's in P. But if it's non-constructive, then it means you may have discovered a new complexity class, okay? And and here is a curious fact. For almost all known problems in TFNP that are not obvious in P, the only non-constructive step in the existence proof, so usually all these proofs, it's sort of eerie, are math, 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 a trivial existential lemma, however, on an exponential graph, math, 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 okay? So, and it's universal, so, I don't know of a counterexample. I mean, all these problems are like that. It turns out that this existential lemma, there are four, okay? 4 star, okay? So, 4 the simple story is for actually, there are a few more. The pigeonhole principle, any graph has an even number of nodes. It turns out here we have, there are some companion classes, like every bipartite graph, if it has a node whose degree is not a multiple of k, then it must have another node whose degree is not a multiple of k. Okay, so to do it for a k different than 2, you have to go to bipartite graphs. Okay, so there is some complexity there. Every path must end somewhere, and every DAG has a sink. So really, these four lemmas are everything we can use. Okay, everything that you can use to prove existential, to prove that functions, difficult functions, are total. And it turns out that this creates some classes. The CLS is a sort of the latest addition 5 years ago with Costis. MP complete is now sort of in the corner, and it turns out that these are inclusions that we know. For example, PPAD is a subset of PPA and also a subset of PPP. In fact, there are oracle separations. Almost everything you see here can be separated by oracles. In fact, and that's new, results, Costis and Ruta Mehta independently, they prove that CLS does have complete problems. And my co-author, Paul Goldberg, and his student recently proved that there is a beautiful natural complete problem for PPA. Okay, and that's consensus having. Okay, it's like a cake cutting problem. And when I say natural, when do we call a complete problem natural? When its input does not contain a circuit, basically, right? I mean, so when the computation is implicit in the input, it does not contain explicit computation. Okay. Good. And there are the rogue problems. Okay, the problems that we cannot classify. Factoring is a rogue problem, except that we have a proof now that by randomized reductions, it's in both MPP, P, and PPA. There is Ramsey, given a succeed graph with a succeed representation of a graph with 4 to n nodes, find a clique or an independent set of size n. Okay, that's, we don't know how to solve it, we don't know where it is, even though we start understanding that it's in PPP. Bertrand Chebyshev, that's my favorite. Given n, find a prime between n and 2n. Okay, we don't know how to do it. And we don't know how to classify it. I'm pretty sure it's in PPP. There is a beautiful proof by Erdős that sort of points in this direction, but there seems to be a lot of work to be done. Okay, PPP, by the way, I mean the parity argument, the pigeonhole principle. So what is wrong with this picture? What is wrong with this picture? It's too cluttered and fragmented, and so that was our motivation. Can there be an all-encompassing class that contains all of this? Okay. The most general and most powerful non-constructive argument in all of math, okay? And to contain all these classes, but please, no cheap tricks, like take the unions of all the classes and call it that's my class, okay? Or take direct products of problems and say, every problem that reduces to, so, do some honest work and find sort of, a class that contains all of this, all right? And so what is the most general and most powerful non-constructive argument in all of math, okay? And when I'm setting you up like this, you know that I'm going to be disappointed, okay? So here is the answer. It's a problem that you call wrong proof. And you are given an exponentially long proof in some logical language, which is presented as a Boolean circuit. When you put I in binary, it outputs the ith line. And that line is either a logical statement and then it says it's an axiom, I'm allowed to do this, or it's a logical statement that says there are some previous statements that from which by another axiom this statement follows. Okay, and you look at the last statement and it says false. Okay, and gives references. Okay, and then you have to find the mistake. All right, so that's the problem. So PTFMP is the provable TFMP is the all problems in NP, or I guess, TFMP, that reduce to wrong proof. And the only question is, which logical language? And the answer is quantified propositional Boolean logic. And it turns out it's not strong enough to prove what we want, and we add functional symbol of the form f of x, y, z as a variable, okay? So, which we axiomatize, these are functions, okay? So we call this quantified extended Frege formula, okay? So QEFF. This is the logical language we use. And the main result is that PLS, PPA, PPAD, and PPP are all subsets of PTFMP. And to show that, for example, let's take for PLS, every DAG has a sink, and the other elementary existential formulas can be proved within QEFF, okay? In other words, that this system is strong enough to prove all these lemmas. And it turns out that this is the hard part, okay? This is what takes 3/4 of the paper, okay? Once you have that, it's fun, okay? Because now to reduce any problem, say, for example, PLS, you are given an input and find the local optimum. To wrong proof, juxtapose. So write down the constant QEFF proof of every DAG has a sink. Okay, we write it's a constant proof. You have it. You write it, and then juxtapose to that an exhaustive false proof of the fact that except that this particular DAG has none. Okay, the DAG in the input. Okay, and how do you do it? You say, well, this node is not a sink, this node is not here is y, this node is not a sink, here is y. So you go through all the nodes, and then in the end you conclude that this graph has no sink. And now you remember what you have proved, and you say, wait a minute, this means this statement proves false. This proof, So, and from these two statements, conclude that false. And now, if you think about it, finding the mistake in the proof is exactly equivalent to finding a sink in the DAG. Okay? In the DAG, implicit in the problem that you are solving. Okay, okay. So this is the proof of the main result. And on the same subject, there is a parallel work in bounded arithmetic by our colleagues Sam Bass and Beckman, and going on through, in parallel with our work. So we've been working essentially around the same years, and contains many similar ideas. We review the papers, they review our papers. We realize that they are not easy to translate into one another. And so we let each other be. Okay, okay. All right. Finally, here is something that has been haunting me literally for 25 years. Okay, so something I could not, and finally I found the answer. Okay, so I want to share it with you. Here are all these things. A pigeonhole principle, every DAG has a thing. If a directed graph has an unbalanced vertex, it must have another. Unbalanced means in degree, different out degree. If an undirected graph has a non-degree node, it has another. And every metered path must end somewhere. Okay, whatever this means, that's CLS. So all these proofs, all these statements, okay, all these lemmas, all these existential lemmas, what do they have in common? Here's what they have in common, okay, and this has been driving me crazy. They are finite theorems, okay? They fail for infinite graphs, okay? Look at them, and all of them fail. If the graph is infinite, they fail. It fails, okay? So, they are only finitary. And the question is, why only finitary? I mean, is there, and there is a reason, okay? There is a beautiful logical reason, okay? Here's the theorem. If an existential argument also holds for infinite graphs, then the corresponding complexity class is in P. Okay, I finally got it. And the proof is an ancient theorem, Herbrandt's theorem, which was in the end shadowed by Gödel's theorem, but it's Gödel's completeness theorem, but it was an amazing advance. So there is a bunch of logicians who are dedicated fans of Herbrandt. Herbrand died in the age of 30 in a climbing accident. Okay, so immediately after he proved his theorem. In a different context, one referee, one reviewer, in ITCS pointed out that there is a very nice paper, very old paper by Ries that has a similar argument using also Herbrand's theorem for something quite similar. Okay, so I should have read instead of agonizing, I should have read his paper. All right. Okay. Conclusion: total problems in NP, once they were sort of remote, exotic, unfamiliar, they are coming of age. They are a beautiful arena of interaction. So I didn't do this in this talk. So but if you read papers about this subject, there is they're a beautiful way of interacting with very elegant mathematics. And there was sort of a quiet decade. Then it was followed by explosion of results, excitement, and insights. And the main open problem is, from this paper, are function symbols necessary for defining PTFP? But there are many other open problems. Is factoring in PPAD? That would make my day. Okay. Are there other rogue problems in PTFP? I'm pretty sure. Are they in PPP? Okay, this would be very nice. Okay, so and for Ramsey, we seem to be getting there. Is Smith PPA complete? Now we have another natural problem, which is PPA complete, but Smith is the following problem. I'll give you a cubic graph and a Hamilton cycle. Find another Hamilton cycle. Okay. Is Minkowski, in a published work with Aviad and others, we prove that among all the pantheon of problems that can be proved by the Pitcher-Hall principle, the most likely to be complete, in other words, the most general, everything else reduced to it, is Minkowski, which basically is given a lattice that is fat, find an integer point. Okay? Fat meaning determinant greater than in absolute value to 1. Okay? That's a beautiful problem. And we very much suspect it's PPP complete. For example, the equal sums, okay, which is I give you n numbers, n integers, find me two subsets that add to the same amount, to the same number modulo 2 to the n minus 1. Okay, that's in Pitcher-Hall principle, but it can be reduced, it turns out, to Minkowski. Okay, so Minkowski is the most general natural problem that we know, and we conjecture that it is complete. All right, so thank you very much. I think I'll give you something nicer to look at. Okay, so, yeah. Excellent. Yeah, I don't know. That would be fantastic. Yes, this should be my, this should top my open problems. You are absolutely right. Yeah, we have been looking. Sorry. Yes, that's right. She's from the Balkans. We are all one. Okay, So this is Zante, Zakynthos. It's in the western, an island in the western Greece. Yeah.
So these statements, right? So like you said that if they applied infinite graphs, then you just get. So are there some statements that are seem existential? They only apply to finite, but they lead to things that are empty. Are there some cases where it's like not obvious how to think?
Yeah.
But you actually can.
So I don't remember. There must be. I don't remember examples, but I'm pretty sure you can. That it takes some, some luck to find. For example, I'm pretty sure there are more than 5 finitary sentences. Okay, so I don't know. But I mean, really, the number five, is not something I'm very happy about. So it would be great to find more such classes. Okay, but it so happened that nobody has found.